the S3 from Amazon account in Clubhouse.
Okay, so what I'm going to do is that I'm also recording on Zoom too at the same time.
Okay, yeah, sure.
So in Zoom, when I record on Zoom, then I can get a video too.
Yeah, perfect. So I also opened up a Twitter Spaces from Science Society just also to try it out today, in case people are interested. But yeah, it's just to try out different platforms, and yeah, it's exciting. So anyways, let's start the room. So welcome everyone to Science Society. We are very honored to have Dr. Liu here with us. And let me tell you a little bit about him. So, you know, some facts about our guest speaker. Dr. Liu is the Dorothy Pate Enright Professor in the Department of Material Science and Engineering at Pennsylvania State University. He obtained his Bachelor in Science from Central South University in China and his Master's from University of Science and Technology in Beijing. And then he obtained his PhD from Royal Institute of Technology in Sweden. And later on, he was a research associate at the University of Wisconsin-Madison, and then a senior research scientist at QuizTech Innovation LLC. He has been at Penn State University since 1990, and he's editor-in-chief of the Kalfat Journal since 2001, and the president there too. And he founded the NSF Center for Computational Materials Design and served as a director from 2005 to 2014. Dr. Liu coined the term materials genome in 2002, and he served also as a president of ASM International and a member of ASM International Board of Trustees. And he received many awards, including the ASM J. William Gibbs Face Equilibrium Award, the TMS Hume Rothery Award, and the Wilson Award for Excellence in Research from Pennsylvania State, and many other awards. And Dr. Liu's current research activities are centered on first principle of calculation, machine learning, modeling of thermodynamics, kinetic and other properties, and the integration of understanding defects, phase stability, and phase transformation, and designing and tailoring materials and processing and properties. Yeah, so we are very honored to have you here. And yeah, thank you so much. The stage is yours.
All right, thank you very much, Catarina, for this opportunity to have some, you know, a little casual discussing about what entropy and Zentropy are, and why they're important in science. Let's see. Okay, I do have a PPT file. So I think Catarina sent the link to everybody. I hope you have downloaded. So I'm going to say the slide number when I go through the slides. Okay. So the slide 1 is the title slide, that is Zentropy.
We don't have the paper yet.
Oh, you don't have the paper yet, the PPT file? Catarina can send the link. The link should be.
Yes, 1 second. It didn't work. Let me see.
No, the link did not work.
While we're working out.
No,
Okay, there we go.
Okay. I'm on club deck today, so I'm sorry.
It's okay. So can you, if you click the link, it should be able to download the PPT file. All right, should we continue?
Yes, everyone should be able to see it now.
All right, so I'm on this first slide. Zentropy. My name is Z Coelho. As Catarina said, I'm teaching at the Pennsylvania State University. This link, www.faces.psu.edu, is our group website. Now I go to slide 2. So Z plus entropy is equal to Zentropy. So this term was suggested by Josh Roberts. He's from the University of Buffalo. I gave a talk in June 2022, talk about our approach. And I said we're looking for a name for the approach. And at the end of the talk, Josh said, you know, maybe Zentropy would be a good name. Then we actually liked it a lot. He explained why Zentropy. This is showing here the link to YouTube video. That's recorded at a seminar. It's about 1 hour long. It's actually at about 1 hour time. That was Josh made a suggestion about the name. If you look at the YouTube, you just quickly go to 1 hour, then you will hear that he suggested. So if you have
just quickly, you know, entropy is related to the partition function.
Yeah, that's right. That's right. That's the next word here, right? Okay. That's why it's Z.
Yes.
That's why we use. That's why he suggests Z, right? Z is Zoom's Zoomi, sum of states in German, and it's for statistics mechanics. As I think as Eric just mentioned that it's about a partition function. It's used for a long time. And it's about a probability of states. So that's basically what Z really stands for. Statistical mechanics means this field. Partition function is the mathematical representation, and it talks about a probability of states. So then the Zentropy is really actually talks to all three of them. Talk about the statistical mechanics, talk about the partition function, and they talk about the probability. So we love this name, so we started using it. So the name is not very old, as you can see. It came up in June last year. Okay, so let's go back to entropy first. Right? Entropy is multiscale. So what does it mean? I guess many of you have read this book or listened to this book by Stephen Hawking, The Brief Answers to the Big Questions. And this is black hole. This is the cover of his book. And in this book and his other publications, he talked about the entropy and information of black holes. So black holes have entropy and you have information. So entropy and information go hand by hand. So this is big scale, right? If you go to a little bit smaller scale, you talk about the human society. It's out of time. Okay, it's another book. It's a very interesting book. Both are bestseller, as you can see. And in this particular book, this author made some very interesting statement. Well, of course, I agree with his statement. That's why I use it. Entropy drives the world. And everything actually basically driven by entropy. So time slows down when moving faster. And then, of course, you probably heard that if you move as fast as light, right, you live forever, because time doesn't disappear anymore. Okay. So that's
get pulled to pieces. This is a theory we have yet to see in action.
That's right, absolutely, yeah. Because you cannot imagine how you travel as fast as the light, right? Okay, that's a very good point. All right, so you can see different scale, right? Of course, you know, I'm a material scientist. I don't study the black holes. I don't study the society. So I study materials. Okay, but it's a very interesting book. So now it's closer to this one, to the materials we study now. So this is a book by Ruth Spiral for kids. She wrote a lot of books for kids. One of them is Baby Loved Thermodynamics. As you know, babies do all kinds of things, right? But one of the things do actually, not only baby, everything we do is processes. Every process we have, it should produce entropy. So one of the big processes we have is the sun, the light, the energy, right? Heat comes from the sun, you know. So what happens here, you get the sun comes the energy from the sun, right? And then the sun comes, reacts with air and water, then produce trees, right? Food, apples, whatever. So it's all by that one. So this, I call this process one. It's light from sun to earth. So that process is entropy production. Yeah, we talk about it later, why it's entropy production. The second process is kids. We're talking about the kids here. The kids make a mess of a house. And anything they do is make a mess, right? So that process produces entropy. So that means the kids actually they're natural. They act naturally to make a mess. Why do they make a mess? Because the entropy is produced in that process. So this is, if you learn the more on thermodynamics, this is basically the second law of thermodynamics. It says that any process, they are irreversible, they produce entropy. Okay, that's second law of thermodynamics. All right, so this is the basic the theory we will have. Then we're gonna you apply them, right? We're gonna apply them. So if you have learned the thermodynamics before, you know that entropy change is equal to delta Q divided by T, the heat divided by temperature. Okay, so let's apply the heat from sun to earth, right? So that means we have two entropy change. One is the entropy change of the sun, another is entropy change of the earth, right? That added together, that's the process of the heat. It comes from the sun to the earth. So now we know that the sun has high temperature, earth has low temperature. And I'm not at slide, I'm sorry, I'm not at slide 5 already. Oh, gee, I'm at slide 5 now, sorry. Yeah, I should have mentioned about slide number. I'm at slide 5 now. All right. So you know,
the one with the title of entropy process, is that the slide?
Yeah, entropy process 1.
Okay, thank you.
Yeah, entropy process 1, sorry, that's right. And so what happens there is that you see that because the sun has high temperature, so delta Q, that's the number of heat taken from sun, divided by high temperature is small entropy. When the same amount of heat arrives at the earth has low temperature. So that is the bigger entropy, right? So the heat is leaving the sun, so the entropy is decreased, but the sun, the heat arrives at the earth, the entropy is positive. So the positive minus the negative, which is small number, the whole process has a positive entropy increase. Okay, so this process is follows the second law and increase the entropy of the sun and earth add together. Because that's one process, right? So that's process 1. So now if you go to, of course, that entropy process, get the energy here, that's where it goes to trees. The tree grows, right? The trees grow and the food, the fruits are produced because that entropy production process. That heat is transferred here and then does all the work. Okay, now we get to slide 6. Get to slide 6. It's a process 2. Process 2 I mentioned before was that the kids make a mess, right? Okay, so what does it mean? That's S equal to KB log omega. KB is the Boltzmann constant. It's actually the Planck actually got the number, but Boltzmann got the concept. So the number, the value of the number is actually derived by Planck, but Boltzmann had the concept, so we call it a Boltzmann constant. So it's Boltzmann times log omega, natural log omega. Omega is the number of configurations. That means how many ways you can range that system. So we give a very simple example. We talk about ice, water, and vapor. That's just process 2, slide 6. So ice, is kind of solid that we see, right? So you cannot easily deform it. So it has fewer configurations. Water is more fluid. You can go all kind of shapes, right? You get a lot of configurations. You become vapor. It's a big area. So you can see that the entropy of ice is smaller than the water. It's way, way, way smaller than the vapor. So to do that, we have that heat, right? You have that heat, gets ice, it becomes water, and more heat, it becomes vapor. So that's how you increase the entropy of the system by adding heat into it. Okay, so what does the kids do? Suppose, if you go to this figure here, this figure is copied from the internet. So at the beginning, your room, it's very tight, right? Very neat. You make the room very neat. And you put the toys here, you put the books there, you put whatever trees there. That's the left side of the figure. When the kids comes, when your son or your daughter comes, and he or she makes a mess, right? Put everything messed up. Okay, so I have a lot more configurations now. So then to the KB, you have after the kids made a mess, it's a log capital N, and before it's low N. So this subtract each other, the total S is increased. Total entropy is increased, the system. So the kids follow the second law. Second is the law of nature. Right? So that kid's good. So if your kids don't do that, you need not worry about it, right? That means the kids is abnormal, but abnormal is not bad too, That's genius, sometimes abnormal at a young age. Right? Anyway, so you can see that when the kids make a mess, it's not too bad, right? It's natural. So then when it's in the evening, you just put it back, right? You put it back. But however, you see, you have this log capital N minus log N. But you remember, you look at the left side here. You have the blue dots. You have the kind of this kind of purple bricks. Then you have this green triangles, right? So each of them have different configurations. So they have different scales here. So you see, it's not just capital N and the small n, right? Actually, I have more things. You have this dots, you have this bricks, you have these triangles. Okay, so I have more configurations. They're different scale. One is big scale and a smaller scale, right? So how do you put them together? So KB log omega is not enough. So you have to consider this one. Okay, so we need a theory to do that. Okay, to multiscale entropy. So that's basically what Zentropy is about. So we need to consider individually and put it back together. Okay, so what it means is that now you talk about the system. Right? System, you have the entropy of the system. First, that you have different microstates. For the previous case, we have three of them, right? One of them are the dots. One of them are the bricks, or four of them. Another triangles. The third one is this gray kind of blocks. Okay, so it's different. So you have a different way to configure them. So you got this PK log PK. So PK is a probability. So then you learn statistics. PK log PK, sum all kinds of possibility together, you get the entropy of the system. However, as I just mentioned, each of the microstate, each of these three or four of the configurations, they have their own entropy, right? Because we should here just one way, because these dots can be arranged different ways, okay, in that small area, okay, or in the whole big area. You can do that. So that means each of them have entropy too. So that means if you want to talk about total entropy of the system, we have to think about two things, right? One is that all those different microstates configuration, that's the first item, is PK log PK summation. And then each configuration microstate has their own entropy, that the probability times its own entropy summation here. So two terms here. So this basically is our entropy. So why that's important? Because previously, as I will show next slide, people only either consider the first one or consider the second one. There has been no theory put them together into one equation. So we see that's a problem. Why is the problem? I'm going to show you next slide. Why is that a problem? Of course, that means the problem is that either one of them is not a total entropy of the system, right? Only partial of the partial entropy of the system.
Hi, can you explain again why the entropy of the system is that formula that involved
this one?
yes.
Okay, this one is okay. If you go to previous slide, go to slide 6. That's kb log omega, right? That's what we typically learn.
Yes.
Okay, but this omega, what it means? That means omega means that all the configurations have the same energy. Okay, that means each configuration has the same probability. However, if each configuration has a different probability, then you get this equation. So you think this one, right? If pk equals 1 over omega, then you go back, you get a previous equation.
Okay, I see. Okay.
So this one was derived by Gibbs back in 1870s.
Okay, I got it. Okay.
So when in Boltzmann case, this equation, the equation on numbers on slide 6 is kp log omega. That's Boltzmann equation. Boltzmann consider each state have the same probability.
Yes.
Okay, that's good. That's a good question. Okay, so most of the textbooks they only teach the first one, kp log omega. They didn't teach this one. They should teach this one first. Then say kp omega is out of this equation when pk equal. Okay.
I think it's because the Boltzmann distribution is easier to derive.
Yeah, exactly. But it's less useful. Okay. So that's good. So I'm on slide 8 now, right? I'm on slide 8. Yeah. So now you have the two terms now, right? The blue term is pk sk summation. That means each microstate. Of course, you have many of them, right? Actually, you talk about a big number. Okay. And then pk log pk is for the configuration among of those different microstates. And then you think about this one, right? Each microstate could have more finer scales, right? So you can make this Si. Now I'm slide 9. Si can have divided even further. So what does it mean? That means this form is so nice. The S equal to 2 terms are together is scalable. It's scalable. You can think about this one. You start from the electron, okay, and then you go to the atoms, then you go to the molecules, then you go to the matters, and then you go to the people, okay, then you go to society, then you can go to the country, then you can go to the planet, then you go to the solar system, then you go to the galaxy, go to black holes. Okay, so it's scalable. That's what we call the nested formula.
So this is the entropy, relative entropy computation of entropy from the relative entropy, right? You can have a conditional probability that you can compute the total entropy as the say of 2 random variables, the x and y, and then the total entropy of xy would be the entropy with respect to x plus the relative entropy of y with respect to x, right? Yeah, so that's actually a very good point. So you have xy, and then you have xy, they have relative probability. So that's why. So the blue term is like x and y separated together, right? But the black one means x, y, they can appear statistically in the system. So they have another probability. Yeah, there's 2 of them. Yeah, so the first black term would be, say, the x with respect to the x random variable, and then the blue term would be the relative entropy, or the entropy of a conditional probability of x conditional on y conditional on x. Yeah, you can think about that way. Exactly. Yeah, exactly. That's also a way to present it. Yeah, that's good.
Sorry, which slides are we on?
It's slide 9. Slide 9. So that's made us very excited. So we can do that. Of course, sorry. That of course, I'm not a social. I'm not doing social study, right? I'm not. Actually, I had a friend he studied forest. He studied ecosystem. And that's actually why about 2019, we wrote this paper, discuss this one. We were going to apply to forest. Okay. I will show you later, a little bit later, what the significance of this equation. Okay, so this is, we call the nested formula. So you can go all the way to quantum scale, then to whatever scale you want to go up. So that's what we found is so exciting about it. Okay, so any other comments, questions? If it's not, I move to slide 10.
What if we,
Yeah, go ahead.
Yeah, actually,
what if we,
can you,
what if we start from the very the bottom layer of
Yeah.
the refinement at a very then your term will be simplified to the original ones, right?
Yeah, then it just has first term. I will show that one. I show that on next slide.
can you actually explain again the addition of the two?
Okay, so when you talk about the different states, right? So what I think about is that, for example, we talk about the room, okay? Talk about the room. So this room is the system, right? There's a system. We have many chairs, okay? How do we arrange the chairs? Okay, that's PK log PK. How many ways to arrange it? Each way has probability. Or you can say in the room, we have 10 chairs, we have 10 people, right? How 10 people arrange on those chairs? So that's the probability there.
Okay.
But then each person has entropy, right? So total entropy will be the arrangement, given way to arrange the people on the chairs. And each person has a probability, has entropy too. So the total entropy of the room would be the way to arrange people, the first black term, and then each person at this kind of configurations and has different entropy because not each person, sorry. So each configuration, because when you go to class, you like to sit together with your friend. So you get a kind of interaction different. So each arrangement of people on the 10 chairs, we have different entropy for that arrangement.
I see. Okay, I sort of get it. But like the two terms, I think it's related something to what Hansen said.
PK is that's PK. Same PK is the same, right?
Yes, but like the two case, I know PK is the same. But like the two sum, are they complete? They are not completely independent or something.
It's actually very interesting. So I'll show you the next slide, how you calculate PK. PK is related to SK. PK is a function of SK. I don't have the equation there, but the PK is related to SK. Okay. That next, actually, is next slide. Let me show you the next slide. Okay. And let's go to slide 10. It's total energy and Helmholtz energy. Total energy is like internal energy, Helmholtz is free energy. Okay. If you look at the classical statistical mechanics, that's by Gibbs, as in the 1870s. And that's what I said. So in that case, it was the entropy of the system is equal to KB, PK log PK. That given arrangement. Okay. And then he derived the partition function. Partition function is Z equal to an exponential of minus F divided KBT. KB is Boltzmann constant. And then because the system has different configurations, right? So it's a summation of all possible configuration. Now here's the total energy, internal energy of that configuration. Okay. So now you see, actually, it's funny, right? This is F, and in the middle is F, Helmholtz energy, but on the right is EK divided by KBT, the total energy. So actually, there's some kind of a funny thing here, right? They're not the same. So if you take the equation I just mentioned, got a Zentropy theory, and on the right side of the slide 10, you have now the purple, the blue one is PKSK minus KB PK log PK. If you go through the same mathematics, the partition function is different. So it's, yes.
Will the quickly again, I remember the important of the original Boltzmann formula. He referred to the omega, capital omega. That's the number of microstates.
Yeah.
It's actually the direct counting of all the micro.
That's right.
So if we are doing at a more abstracted level, say one level above, say you can think of FEA. I mean, you cross screening and you get less refined. Then on each level, the number of states
It's different.
will be incorrect.
It's different. It's different. Yeah.
Different. And I thought that it's supposed to be at the most bottom level.
That's actually you're right here. That's the last line on slide 10. These two are equivalent when S equal to 0. So when does S equal to 0? It's for pure quantum state. So if your microstate is a pure quantum state, then S equal to 0 because they only have one state. Log of 1 equal to 0. That makes sense?
There's no variability at that point. It's just one state.
That's right. That's pure quantum state. However, the pure quantum state actually has a very interesting definition, right? What is pure quantum state? It's one state. Okay, that's first one. And it's at 0 Kelvin, right? Okay, now if the pure quantum state is at a high temperature, what happens? That's the first question, okay? The second question is that when people apply the equation, the original one, nobody started with pure quantum state. Do you know why they cannot do pure quantum state?
Tell us.
Because that means you will solve Schrodinger equation. That's basically Schrodinger equation is about. Schrodinger equation is about all kinds of states you have, all interactions. So basically, if you want to apply the left equation, it's okay, that's fine. So you have to start with the pure quantum state. Then you basically have to solve the quantum mechanics equations, Schrodinger equation. But of course, we know we cannot solve a Schrodinger equation. But we can solve one simplified Schrodinger equation. I guess some of you know that equation we solve, right? That's theory. Do you know what theory we use to solve a Schrodinger equation today?
Well, I mean, that depends on how many particles you have. If you say like you can always start with the original equation, Schrodinger equation, and then compute everything.
Yeah.
And, or if you deal with the molecule, then you have density function theory, and then
Exactly.
you can always,
Exactly.
do and then if you do the nuclear physics, then you have shell.
Yeah.
Shell theory.
Exactly. Absolutely. That's great. That's great. Thank you. Thank you. That's exactly the point. So today, if you want to solve any real material, what even not real, if you want to solve beyond the hydrogen, okay? So you have this density function theory to do that, okay? So now as soon as start to density function theory, you don't have pure quantum state anymore.
Well, I think what level you're trying to compute the entropy. I mean, in theory, well, for first principle, you can always compute the entropy from the most basic particles.
Yeah, for electrons, right? For electron density of states of electrons.
Yeah, right. Electron or even from quarks. it's from the very constituent of the nucleus and
That's right.
So, but let's say the thing is that if you do not, there's no change in the process. Let's say the initial stage and then final stage. If there's no change, well, actually the absolute. I don't think we compute the absolute value of the entropy.
Oh, that's an excellent point. That's an excellent point. I think,
Difference.
yeah, you made an excellent point here. Okay, so now, so what is density functional theory? Density functional theory states that at a ground state, at 0 Kelvin, okay, at 0 Kelvin, there is one ground state. That's a pure quantum state. Okay, so for that pure quantum state, there's one specific electron distribution called electron density. So basically what it means is that in it, because you cannot track individual electrons, okay? So we can say, okay, but we have the electron distribution in the system because of the electron density. But we know that the theory is that there must be one electron density distribution, and it gives the ground state. There's only one ground state. That's what density functional theory is about. Okay, that's very good. So that means now we're going to calculate that one. That's the distribution of electron. Okay, we got the ground state, right? Okay, that's fine. However, as soon as you start the temperature, as soon as the temperature is not 0 Kelvin, what happens? You have two contributions now. The electron densities will be different. So you get electron structure. You get the Fermi-Dirac distribution for electrons. Okay. Second, you got a phonon. What is phonon? Phonon is the atomic vibration. So you get the two distributions. Okay. Of course, you have two serial for that. You have the Fermi-Dirac distribution for electrons because of the Pauli principle. And then you have the Bose-Einstein statistics for the phonons because they are indistinguishable particles. So from density functional theory at a finite temperature, what do you get? You get SK. For each state, for each configuration, you got a SK. SK is a function of temperature. So now you see that as soon as you go beyond 0 Kelvin, you get so many quantum states mixed into one state. So if you can do DFT calculations for all of them, okay, and then you have the some electronic contribution if it's conductor. Of course, if it is insulator, you don't have electronic contribution because the electron, the Fermi level is 0. And then you have, but you still have phonon. Okay, so that what goes to the SK in this slide 10.
Professor Liu, I think this is a very key point. We should be kind of to repeat what you just stated about the definition of the.
That's a really key part. Absolutely.
SK, yeah.
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 So
Appreciate it.
yeah, so the SK here has. If we start I think it was Erica, right? Somebody mentioned it was Erica, right? Yeah, somebody was asking. So as a today's theory, okay, if you just go to theoretical part, go to Schrodinger equation, the left side is perfectly okay, but you cannot solve it. There are too many states. Okay. Based on density functional theory, to solve the Schrodinger equation, we have to have SK on the right side. Unless you stay at 0 Kelvin. Okay. As you said 0 Kelvin. Of course, at 0 Kelvin, you don't need a partition function, right? That doesn't matter. So that's really now go slide 11. That's what we talk about here. Yes.
So is SK defined similarly as before? Basically, also
Yeah, actually, that's exactly. So SK.
You need to microstates.
Yeah, that's right.
Specify.
That's right. But in SK, when you calculate SK, we just need to pick a log PK equation. Not exactly, because for SK, we need two distributions. One is the Fermi-Dirac distribution for electrons. That get by electron density, right? Electron structure. And then we need a phonon. So with both Einstein statistics for phonons. So S has two contributions. Electronic contribution and the phonon contribution. So both of them are pure states. So their individual SK is 0. That's the beauty of it. That's the beauty of density function theory, basically, really.
Well, they are together, right? Because
Yeah, that's right. They're put together. SK equals summation of these two.
that, I mean, the two phonon and the electron, they actually exchange energy. I mean, at the key point, and I guess the key question is how they reach the equilibrium temperature.
Oh, so that's actually very, yeah. That's right. That's a good point. Good question. So what happens is that, so, you know, if you just do DFT calculation, you get 0K energy, right? You get an electron distribution, okay? And you have the density, sorry. And then you have to go to finite temperature. As soon as you go to finite temperature, you're going to have the partition function as you show on the slide 10 here. Z equal to summation of EK divided KBT. Okay, when you do that one, so you calculate EK by the density function theory for all the electronic contribution configuration, for all the phonon contribution.
I see. So the SK, I can think of as subsystems, like composing the whole system as, for example, the electron component versus phonon component.
Exactly. And this beauty, right? Both of them you use the partition function on the left side because they're pure states, pure quantum state. You cannot divide the phonon even further, or at least in the quantum mechanics theory. Okay, so we're leaving the quantum mechanics theory. The phonon and the electron are both pure quantum states. So that's the beauty of the left equation works for it, works for both. So the left side calculate SK, put it this way, all right? And then we add on top of that, we'll put a PK log VK.
In Boltzmann's I think language, you would actually treat them as equal. I don't know. I mean,
yeah, that's right. So Boltzmann treated PK equal to 1 over omega. That's right. But in principle, it's incorrect because we know if you do quantum mechanical calculations, they're not the same energy. So PK is different.
So basically, it's basically you do the maximization of the Gibbs tree energy with respect to the probability, and because of the convexity of the function. Of course, I mean that basically it's when you hold the energy constant, then you basically get the maximization condition gives you the Boltzmann.
That's right. Exactly. Exactly. No, it's maximize the entropy, minimize the free energy, right? So it gives the same results. You can minimize the free energy on the F. Okay. Okay, you minimize F, you got the PK. Or you maximize S, you get PK. Same thing. They get the same results.
Yeah.
Okay, and that's fantastic discussion. I like it.
So the thing is, I suppose you're gonna do the optimization at different levels, right? Each
yeah, that's right.
Subsystem.
That's right.
Yeah. Otherwise, if you do well, the thing is, I mean, it should be consistent with the if you maximize the whole thing as one ensemble, and as opposed to if you just set each subsystem as a closed system and then maximize or minimize the free energy in each for each subsystem. Right? That's
actually an extremely important question I asked here. Okay, the first equation S is independent of ensemble. Okay, ensemble only affects what free energy you use. So, for example, if you take MVT, right? Canonical ensemble, use F. If you take a Gibbs ensemble, use G here. So only difference is this partition function. The entropy itself is not affected. Same formula.
Yeah, I have a question here. It seems to me like you define this one is very weird because like the two components they mixed up, you know, like one macroscopic pack is mixed up with the one level below it.
Absolutely. You are
and you know, like why don't you like treat them separately? Why do you sum them up in the first place, you know? And then, you know, if you go down further, you know, it's the effect of the each contribution, you know, how do you what's the usefulness of that approach, you know?
let me tell you that one. So that's actually a good question. If you go back to slide 9, you see that importance here. Because it's practically useful. Actually, next slide, not slide 11 too, but let's talk about slide 9. It's practically useful. When you do experiments, right? Suppose do X-ray, for example. You have a resolution. You have two resolutions when you do experiments. You have the time resolution and the spatial resolution. Okay. So when you talk about your results from your measurements, you actually define the scale already. Okay. So for example, if you use X-ray to measure magnetic properties, you cannot differentiate individual spin. You measure the system spin, the macroscopic, instead of microscopic. So it's really because of the experiments we do. Because in any experiment, we don't measure all the scales simultaneously. We measure one scale. All experiments one scale. And all the other scales, it's summed up as the data you have. So you don't measure individual scales at each measurement. So that's why I divided them. For example, if you do neutron scattering, if you do the synchrotron, okay, then you measure different scale. Then you need to have different scale, the equation here. You need to do two different scales and line up. Actually, you guys asked just so many good questions. For example, I don't know how many of you know ferroelectric, later titanate. Later titanate at low temperature is tetragonal, polarized tetragonal. At high temperature, cubic. That's by X-ray. However, if you do another measurement with much finer time and space resolution, at all temperatures, they are cubic. They're tetragonal. There's no cubic. Okay. So it's really the homogenization by experiments become very important. All right.
So basically,
yeah.
If I so basically you
yeah.
Basically if you're looking at the different or scale or level where the lower level is not perturbed, not interacting with the higher level.
Exactly.
So you just just change the higher level configuration.
No,
and that the lower level is not interacting.
No, they are interacting. No, they are interacting. No, they are interacting, but it's your resolution cannot see it. You see the average behavior. For example, I just let's go over to slide 10 again. Go to slide 10, right? The left equation is correct if you start with the pure quantum state. That means if your experiment can sample all the pure quantum state, the left equation is correct. However, if your experiment cannot sample each pure quantum state, then the left equation is incorrect. You have to use the right equation, right side equation.
Yeah, but the thing is, if you have pure quantum state, it is changed during the process.
No, it's not. Pure quantum doesn't change. Electronic state doesn't change.
If it is changed, let's say, I mean, I can make let's say, photon, very high energy photon, and it destroy or the state in the lower level, then there's an interaction, right? So the state changes, then I have to compute that entropy. I mean, compute that.
Absolutely,
state.
you are right.
Count that
Yep.
state.
You're right. Yeah, you're right. For example, if because see the left of equation is the base state is pure quantum state. If you say you go below the pure quantum state, right? Then there's more states actually. You're right. Yeah, you're absolutely right. You can go.
So there is.
Yeah.
Yeah. This is basically, yeah, it's looking at the most to make it more efficient in calculation. Right? The which are not those which are not changed, you don't count for it, because the final result matters only the change in the entropy matters, and not the absolute value of the entropy, right? So whichever level that is changed, you account for it, and then within like at a smaller scale, smaller resolution or higher resolution, if it is not changed, why do you want to account for it, right? So the only you investigate on when it is needed, when the if there's any change in the finer scale, right?
You can think about it that way, but if you take the left equation, you take the same state to calculate, you get wrong results. Okay, that's actually next slide. That's the next slide 11. Okay, so you do experiments, you measure thermodynamics, you can measure heat capacity. You can measure it. You measure heat capacity, you do integration, you get entropy. You have to put the two together to get the right entropy compared with the experiment. If you don't do it, you cannot. That's why in the literature, nobody can predict the heat capacity for this kind of system. So you take each part of it. So you see, the red part is the quantum mechanics. If you take quantum mechanics alone, you cannot the result will not agree with the experiment. If you take the blue statistical mechanics alone, you cannot agree with the experiment. Okay.
It seems like really like you said at the beginning, like multi-level.
Yeah, it's right.
So the macroscopic one, the entropy, it doesn't automatically contain completely the lower scale, right?
Absolutely.
So that's why you have to take into account the lower scale when necessary. That's basically.
Yeah, you're right.
That's what he was saying.
Exactly.
Yeah, necessary. What's defined as necessary is when it's changed. If it is changed, then you have to take into account. You have to just investigate and take account for it.
But there's no case. But there's no case you can take the blue term the blue term only agree with the experiment. It doesn't happen. The reason is because you always have the red term here.
Did you apply this to some real experiment?
Well, of course, we have many of them. Okay, I've showed. I talked about some expansion and the quantum criticality. That's next the slide. No, I want one more slide. Slide 12 before I go to the results. So now we need to make it more general about entropy production. Okay, entropy production. Now I divide them into 4 terms. The first one we typically talking about is the heat, the red one. But as a human, right? Human is a system, or any actually organisms. You have to consume something, okay? Then you produce something, then you produce information, okay? So the heat is generated, the nutrient consumed, waste generated, and the information destroyed. So that's the total entropy production of any process. Now we can apply this one to the cases, okay? This is one. I want to show you one example. The cerium. Cerium is one metal. So now it says this is phase diagram. If you have heard before, water is phase diagram, right? Temperature, pressure. You can change the volume to pressure. That's just like a temperature pressure phase diagram. But if we want to do the volume, some expansion. So now what happens is that in water, water and the vapor has a critical point, right? Okay. So that's critical point here. Same thing. At the critical point, volume expansion, V to T derivative diverges. That's the definition of a critical point. The system becomes unstable. When it's unstable, T to V goes to 0, V to T goes to infinite derivative. So all the lines are prediction from our model. And the dots here, the symbols here are experiments. This is without any fitting parameter. Just use the equation I talked about. Calculate DFT with the quantum mechanics calculator and the statistical mechanics put them together. We'll put the critical point. I will challenge you if you tell me anybody has predicted the critical point in the literature without any fitting parameter. This is magnetic transition critical temperature. That's fine, right? The volume expansion. But I want to give you another dramatic one. It's on the right side of the diagram. So this temperature volume. So each line, each curve here is for fixed pressure. So this is the one is you see the one with zero pressure, that means ambient pressure. Okay. Now, if you look at the right diagram for iron-3 platinum, iron-3 platinum is the IMA alloy. IMA alloy was discovered about 1890 something by a Swiss scientist. He got Nobel Prize because he discovered it. So in that alloy he discovered is iron nickel, iron-3 nickel around. The thermal expansion becomes negative. Thermal expansion is not a phase transition, is not a two phases, still single phase. Okay, you see this one on the iron-3 platinum, you have this black dots. When temperature goes up, volume first increase, and then increase less. And then with the proper the symbol range, it becomes zero. Then decrease the volume, temperature goes up. And then decrease less, then becomes zero, then increase again. If you increase the pressure, and the line moves to the left and reach the critical point, that's the volume negatively diverges. Okay. So that's completely predicted by our theory, about the Zentropy theory. And again, there's no fitting parameter. You take the DFT calculation for number of states. I will give you so surprised, right? For the cerium, we won't have 3 microstates: non-magnetic, ferromagnetic, and antiferromagnetic, a different spin configuration. For iron-3 platinum, we have 512 states, different spin configurations. So this is application. Again, the symbols are all from experiments, and the lines are purple symbols are from predictions. All right, that's all I have. Wow, I think 1 hour. That's good.
That was great.
Excellent talk. I had a question.
Now, I want to mention one more thing. Okay, so that's why I think this can apply to society, right? You know, society is kind of homogeneous, but when that society becomes unstable for the good reason, unstable for the bad reason, but for the bad result. If I consider the positive, but it is bad, right, so to speak. You get a huge expansion of the volume of society, or huge contraction. So contraction means that society destroyed. Expands that society expand to conquer other places. So it's a pretty one. It's the instability of society. So that's why I think it can apply to society too. Big Bang is instability, right? Or the black hole is instability. That's actually what the
collapse of civilizations.
Yeah, collapse of civilization.
Due to these dynamics that you just described.
Yeah, exactly. And actually, you see, if you have listened to you read the book by Stephen Hawking, his focus point of his theory is singularity. The critical point here is a singularity. All right, singularity. That's the end of the story. Thanks everyone.
Yeah, thank you so much. That's great presentation. But please go ahead and ask your questions. Tuan, Dr. Shah, you didn't get the chance to ask a question. Please go ahead.
Well, okay. So this, some of this reminds me of some, work. Well, molecular dynamics is very much approximate, but getting into a deeper understanding of hydrogen bonds. I remember a science paper, in an electronic structure, we'll make a Born-Oppenheimer approximations, which says that while the nuclear motion is so slow, the electronic configuration can just adjust to it. And so we can separate those two calculations and ignore the coupling. But in terms of a particularly interesting science paper on experimental paper on hydrogen bonds in proteins, it was shown that the hydrogen on the donor going to the acceptor will end up tunneling back and forth and will have a resonance time of somewhere around 10 vibrations within the acceptor donor pair. And it struck me as how inaccessible our present theories or methods of calculation are to really get to the energetics. And as I'm listening to your talk, it seems like there might be a novel approach to the accounting and the energetics there. You have any comments on that?
Yeah, it's absolutely. I fully agree with you. So you see, all the work we do now today, most of the work, okay, is that we cannot predict. We cannot. You see, there's no closed mathematical form for singularity, right? Because you have to go through singularity to other side. So you cannot have one mathematical equations go through. You cannot have one Hamiltonian to go through the singularity. Diverges. Okay. So that's the fundamental problem we have, all the mathematical representation. So in this case, we have here, in principle, if you want to get a very, very sharp singularity, you have to have an infinite number of states, right? Okay. Configurations. So that's got a, because that's what they say, with the singularity, your wavelength becomes infinite, basically. Fluctuates everywhere. Okay. But in the reality, of course, when you approach that singularity, it's not an infinity yet. So our approach basically say, okay, when you approach that point, you can see that it starts to diverge. Okay. So if you want to make it a very sharp diverge, then you can actually predict it. So any Hamiltonian approach has a limitation. You cannot do that. So that's what I said. There are two parts of our equation. The first part, for individual well-defined configurations, you can calculate them use density function theory, is quantum mechanics, well-defined. So the singularity really originates from the competition of different microstates configurations. That competition is represented by the second part of the equation. So you have to have both equations together, both parts together in one equation to predict singularity. Otherwise, all the theory you can describe a singularity. You can say, okay, I'm going to describe it, use this formula, right? Then you say the divergence there, but you cannot predict it. I hope that answers your question.
Yes, thank you.
Dr. Liu, I had a few questions. One, we're a little bit past the top of the hour, so just wanted to check in with you, see how much time we have left with you. And number two was, what drew you to science? What was the first thing, or how did you end up a scientist?
Okay, that's a very good question. Thank you. I like to talk, so I think I can talk another half hour, 1 hour if that's necessary. All right, but I have to do housework after that too. Okay, that's okay. Okay, so I grew up in the mountain area in China, remote mountain area. I was told the grown-ups told me when I was young. I always ask people question why this, why that, why this, why that. I don't know why I do that. So I have this curiosity. I want to understand why things work, how things work. That really pushes me. So in China we had a cultural revolution when I grew up. So I didn't have much education, so to speak. China, the university in China were closed from 1963 to 1973, 10 years. There was no university basically. Okay. So in 1976, they started to say, oh, maybe we should do something now. And in 1977, they said, okay, let's open university again. Let's open universities again. So I was first in high school at that time, and then my principal, and university principal, the high school the school principal, he said, maybe it's great. You want to try to take the exam to go to college, I said, okay, I didn't know. So they said, okay, let's do that. So I didn't finish high school. So I went to take the exam. And I passed the exam. So I get into college before I finished my high school. Of course, that's abnormal, right? Because that's just the time history. And then when I finished my college, 4 years, I like to ask question again at that time. I like thermodynamics. Okay, the thermodynamics was my favorite class. But I have to tell you that the teacher was pretty bad that time, and his teaching like made everybody sleep in the class. Anyway, so I really liked thermodynamics. I took that one, and then when I finished college, I need to decide what to do. Right at that time, again, they started open grad school. Okay. Grad school actually also started in 1977, 78, but very few people can get in. And then my father said I should get a job. He actually got me a job to work on, but I said, no, I want to study more, understand more. So then I took the exam, I got the grad school. Again, the reason I got into grad school because I did well in thermodynamic exam. And then I met my wife, I got married, she was my classmate. And then I continued to get my master's degree, then my wife went to Sweden. I followed her to Sweden and get a PhD. Yeah, I always like to talk with people, talk with ideas, ask whys. Then I said I had to become a professor because that's where I can really freely ask questions and teach people about knowledge too. I've been in Penn State about 23 years now.
Professional asking the question why. Yes, that's one of my favorite questions.
Yeah, I really like that. Always. So when my students here, I graduated students, right? So I tell the students, you have to ask 3 whys for one question, or one issue, right? If you can answer all 3 whys, then nobody can ask you question anymore.
What are those 3 whys?
No, 3 whys is that, for example, why do you do this, right? You do whys, then you go with 3 levels, just multi-scale.
Multi-scale and nested.
Yeah, exactly. Nested 3 levels of question, whys.
My favorite question. Who else has questions?
I have a question. So thank you so much. First of all, that was a very fascinating paper. My question is about the configuration, because you just explained a couple of the, equations that you just used previously. So the configuration part, does it have a use in for the black hole?
Yeah.
Configuration or not?
That's right. So if you, of course, again, I'm not a black hole expert, but very kind of a very simple understanding of this one is that in Stephen Hawking, and actually before him, there was another a young person. So that's what I know that many young people here. The young people have a lot of ideas, right? So when they try to figure out the entropy of black holes, they did a lot of mathematics, okay? But their conclusion was that entropy of black hole is proportional to the area of the black hole. That's the final conclusion. So what does that mean? So what is on the area of the black hole, right? Think about this one. Okay, so is Shah, right? Shah, was Shah you answer the question?
Yes.
Okay, Shah, what do you think? If you talk about the area, right? The entropy is proportional to the area. What does that mean?
What does it mean?
Yeah, right. So entropy we talk about the entropy is Kp is peak log is Kp log omega, right? Omega is the configuration,
Yes.
number of configuration.
Yes,
Yeah, but in their equation, they derived and say entropy is proportional to the area of the black hole.
Actually, the area of the black hole, it doesn't mean that much. It doesn't have that much meaning to me, because in a certain point, we're gonna have the infinite.
Yeah, so that's right. So it's exactly right. So what it means is that you have a large area, you have more way to arrange your stuff. So you get more high entropy. So that's what the black, at least at the moment, the black hole entropy is like that. But I really like to do, if I, since this news published, I know you guys found this one too. It's really that the nested form, right? Actually, I got an email from a cosmologist, and he said, "Oh, maybe he want to apply this one to the black hole." Actually, no, he want to apply this one to dark matter. He said this can be applied to dark matter. So I'm waiting to see whether you can
I
get.
think you answered my question, but I mean, in another part, I mean, I was just wondering about the producing the data, because when we are thinking about the, I mean, quantum level, it's different. And when we are talking about the data producing with the matter that you just explained, that's a different level. Because even in the biology, in the system biology, even sometimes I think that it's possible to produce the data based upon the equation that you just explained.
Yeah. So in the biosystem, it's so complex, right? So it's really a much bigger than the problem I'm addressing, because in my case, I address atoms, and that I address the magnetic spins and the polarizations. If you go to in my opinion, if you want to truly predict the biosystem, you need to start from the quantum first. You calculate the molecules, then you calculate the molecule arrangement, okay? So then you have these different configurations together. Then you talk about how the molecules will arrange them in the space. Then you have this at least 3 or 4 levels more than the one I present here. But I still think it's important thing, in my opinion, is you really have to you have to account all the entropies which play the role in those biosystems. If you just take one level, like many people do, that's insufficient. It will not give you the predictive power you have.
Did you ever consider it? Did you ever consider the full configuration?
Yeah, that's right. But you need to. But you see, but it's so complex. You cannot put all the configurations at different levels together. You have to separate them layer by layer, level by level. Then can do it. If you so see, that's why the original statistical mechanical equations cannot be used. The people use it wrongly. Okay, they didn't use if you want to really use the original one, you have to do all the pure quantum state. That means you have to solve Schrödinger equation for everything. You cannot do it. It doesn't work. So people didn't use that one. They used the non-pure quantum state. They apply the equation. That's one application of this state. So in this case, we say, okay, let's separate different levels. So which level we can predict, we can calculate, then put them, then stack them up, basically. So I think it's the same for the biosystem. You have to stack them up at the different scales. Then you can truly predict the performance or the properties of a molecule or of a organism.
So if we compute the Gibbs distribution, which is as we discussed before, which is the maximization of entropy or minimizing of free energy. If we look at the distribution, computer distribution at a certain level, which would be let's say a coarser demarcation of the states. So basically, you have the coarser demarcation, say the subsets of the state space.
Yeah.
And so if we do the same thing for maximizing the free energy, maximizing the entropy or minimizing free energy, we should get the consistent distribution. And I think the demarcation or the selection of the subsets, there should be condition on the selection of the subsets, right? Or in other words, in physically speaking, how we define a level as opposed to another level. I suppose we cannot just arbitrarily select the subsets or the arbitrarily demarcate the levels, different levels, and then just do the maximization or minimization in that level. Is that correct?
Okay, so that's actually a great
Needs to be
question.
a
That's
definition
a good
of
question.
these
Okay.
levels.
Yeah, that's a good question. But I think it doesn't matter, in my opinion. Let me explain why it doesn't matter. Okay. So if you look at the slide 10, right? Let's say I think it's slide 10. Just make sure I get the right slide there. If you look at the slide, slides 11. Slides 11. That's fine. Oh no, slides 10. That's right. Slides 10. So if you can access all the pure quantum state, you can get all the properties of them. Then you can use left side equation, right? Okay. So now the right side equation is basically the assemble, the high level of the left side equation. Okay. So you put them some together. So what does it mean? That means so basically from left side to right side, the infinite number of ways to combine them. You can combine any way you want if you can get the data. So the two.
I agree with the first equation, how you compute, given the probability states, this is always true. It's just the getting the entropy of two variables, two random variables from single one of them, and then combined with the conditional entropy. And this is always true given the probability. What I'm kind of concerned about is the second line for the distribution, because the distribution comes from the maximization and or minimization or whatever optimization you do to get the distribution. So if you take
I have the answer for you. I know your question. I have the answer to you. Let's see. Let me give you an answer, see if it's correct. Okay. So you want to use the right side equation, right? So each K, that state, must fill the whole system. That micro state cannot be part of the system. It has to fill the whole system.
Which slides are we? Which equation?
It's slide 10. Okay. So that SK, right? And SK is very important here. And SK, because that SK represents one microstate, right? That microstate is not a pure quantum state. That microstate must fill the whole space of the system.
So basically, the microstate has to be interacting with the whole system, right?
You have to interact with the surroundings. Yes, right. Have to interact with the surroundings. So I have to experience the same constraints as the whole system.
Yeah.
That's exactly what you mentioned. Because if you take a microstate is not experience the constraint for surrounding, the right equation is incorrect.
Yeah. So then I'm just looking at trying to understand the meaning of the Z on the right hand side.
Yeah.
Especially the summation in the summation notation.
Yeah.
On the exponent you have FK, right?
Yeah.
So and I suppose the FK. So if you're interacting with the rest of the rest of the environment, the rest of the system, which is called environment, then the FK. So so of course you can make the FK as a kind of a variable, right? Depending on what the environment gives you, yeah. So if it is it is given by the environment or computed from the environment, yes, you can always make the everything consistent. With my motivation of the question is, I'm trying to see if I can make everything consistent, because it seems to me that you're trying to basically do this because to make the computation convenient, we do not need to compute the whole system, but just the part that we need, the level that we need. And I'm trying to see that, or prove that under what condition that we can isolate that level and do the maximization and or minimization within that system without bothering the environment or the rest of the system. Or of course that we can use a few parameters to represent the environment or the heat bath. So I don't know which approach you're taking, the one or two parameters to represent the heat bath, or making this completely the level completely closed.
Okay, so what it means is that when you talk about the interaction with the surrounding, is basically the ensembles, right? So
Yes.
So as soon as you fix the ensemble, you fix the free energy. So that's really just the go back. So if, for example, if you do the MVT, you get harmonic energy. If you go to the MPT, you got a Gibbs energy. If you fix other variables, you get different energy functions.
Yeah.
Hansen, Hansen. So I think like the thing is, statistical mechanics as taught in textbook is still correct, because like all the formula you see that they apply to ideal gas system, that they are able to reproduce, the ideal gas equation and things like that from the quantum distribution. But I think in the case of what Dr. Lee showed today, he showed that for some system, for some real system, where you do measurement and things like that, you don't see, the experimental data, agree with the theoretical calculation unless you add, more stuff, right? And so that's why his formula comes in. So I think that eventually the question is really about, whether or not his formula applies, correctly to experimental data, right? Is it that's the?
No, I'm not saying that the formula, the statistical mechanics is correct, and the maximization, basically the distribution comes from, of course, I mean it's the equilibrium state, and then we're not talking about the non-equilibrium state, right? And then equilibrium state, and then so basically you look at the whole ensemble, and then if you optimize the system, you get the distribution. So the thing is, in principle, we're done. The job is done. But let's say if we if we try to make the computation more convenient and faster, right? So some of the computation we don't need to deal with the whole system. That's what I think the motivation of this research is about.
No, you still deal with whole system. No, you still deal with whole system. You still deal with because you still have to start from the quantum state. Okay, but the only thing is, but the only difference is that you put those pure quantum state, add them together as one macro state. That's the only difference. So as I mentioned,
so there's still some practical issues in computation. Even when let's just go back. Okay, we'll start at 0 Kelvin and we'll start to heat something up.
Yeah.
I mean, if you get a system, well, to handle the electrostatics at a larger scale, you like to employ periodic boundary conditions. but we're not going to be able to, some of the finer details are going to be aliased in when we go in and out of frequency space for that. And so we're not going to be able to capture all the terms that we need, right?
No, you
We're
do
gonna
catch.
need
You know,
some-
you catch all the frequencies. You catch all the phonal frequencies. You capture all the electronic frequencies too, but the density.
But we have to impose the periodic
Oh,
boundary.
that's right.
so-
That's right. Oh, you don't have to do that because you can do the molecules, right? You can Gaussian distribution. You can do the single molecules too.
Well, for a patch of material, as you scale up, I mean, say, let's go up to 100,000 atoms. or
Of course,
something.
then you cannot do it. Of course, that's beyond your scale. That's right. That's right. You have too many states. That's right.
But even if you're down to a smaller patch where, say, okay, you got your exascale project funded and you're going to go
That's right.
compute these things.
That's right. That's right.
But you're still, the long range electrostatic, you still have to apply these periodic boundary conditions. And so, well, yeah, you're stuck equilibrium and you can't study wave, heat traveling, you can't have asymmetric boundaries if you're going to go periodic. So-
Yeah, I agree with you because the density function theory, when you want to make calculations, you take the periodic boundary condition. That's right. That's right.
So we won't have all the right states to add up to even apply your formula to.
Yeah, but I see, the most of the problems we have, right? Most of the problems we have, first, they are relatively short range interaction. That's one thing. And if you do have the very long interaction, like you just mentioned, electrostatic interaction, very long range, is way beyond the supercell we do, right? But it turned out we have a solution for that too. So what you do is that you don't do it in the real space, you do it in the reciprocal space. That's the beauty of it. We have actually a paper on that, a few of them. So what do we do? Let me tell you, see if you see that solve partially of the problem. So in the real space, you do the periodic boundary condition. You know it's incorrect because the long-range electrostatic interaction is not considered. And then you do that calculation. Okay, so how do you want to how can you consider this long-range interaction? So what you do is that you go to reciprocal space. Now this will become very interesting now. Why is it interesting? Because the infinity distance becomes the origin, the 0 point. That solution is analytical. Okay, so now you can take the analytical equation, like the solution you have, you can add on top of your a real space periodic boundary condition. And of course, then you still have a problem, right? So what is the super between the superset and infinite? Okay, then you do some interpolation. It actually worked out pretty good.
What I find confused about this, not confused, but like when I look at this formula, I feel it's a little bit strange because it's not it's not based on any theoretical foundation, right?
Which one? I mean this one? You mean the Zentropy?
Yeah, the Zentropy, like your.
Oh, it is. It's exactly okay. You look at this entropy, right? That's exactly on our slides. If you look at the slides, start from slide 7. Okay.
Yes.
If first slide 7, that's exactly fundamental you start. It's purely theoretical derivation, no assumption here. You start with the system entropy. You say, okay, system has different microstates. This microstate is important. It's very important. I think it was Hansen said that once. It's very important. Each microstate here has to experience the same constraints from the environment as a system. That's why you can apply this pk log pk. Okay. So now, the next thing is that, okay, this is only part of the entropy of the system.
Yeah, but like the addition fact it seems to me it's very heuristic, That
Oh,
is
no,
not-
wait. Are you saying that? Sorry, Tom. You talking about the page?
8. Go to page 7, 8, 7, 8, and 9. Right, 3 pages.
Yeah, 3-page. The equation. So you're saying that the plus sign, the blue, black, summation plus blue summation is strange.
What I'm saying is, is is a heuristic formula, you know.
Oh, no,
Is-
it's not. It's not. It's the, so basically the two sums. So basically you have a the blue so like the black one, the black one is a kind of a coarser level, the entropy, and then the blue one is a finer level.
Yes, but like there's no you know principle to say that you have to add
Oh
that
yes,
up, you
there
know.
is principle. Okay, yes, I can prove it to you. I mean, this is, oh, you can just look up the Wikipedia information theory, the entropy. So the relative entropy formula that the entropy of xy is equal to entropy of x plus the entropy of y relative to x.
So Dr. Lee, so you saying that your formula, the addition, it is, you know, coming from first principle. It's not a heuristic formula. Is it a heuristic formula, or is it, you know, did you derive it from first principle? You know, some first principle. Like, what are you saying?
I
Heuristic formula, or is it, you know, did you deduce it from some first principle? That's what I'm concerned. Because if you, you know, deduce this, if you you know, derive it heuristically, it means that, you know, that you will eventually, you will see system where it's not applicable anymore, right? Or you will come to situation where, you know, your formula is not correct anymore. You see what I mean? Like, it's not theoretically based, and so you don't understand exactly, you know, the conditions that, you know, that will make your formula correct. Like, you don't have a complete understanding of that. Is it true?
I don't agree with that. I think one thing here, this one equation looks like it's discrete, right? But it's not discrete in principle. It's actually continuous. Continuous means that you can think about the at any given condition, what kind of states that a system could have. You can do as many as system you want. You can infinite number of configurations possible. Okay, then you get a first term. They can range them in space based on the probability, and then each state it's just like the first law. It's like first law. Okay, first law is energy conservation. This one is about entropy, a combination of the system. It's how you can divide the system into all possible configurations. You can imagine anything you can imagine. Okay, then you get a first term, you get a second term.
Okay, I see. Okay, so you are saying that it is its status is like the status of the first law, where you cannot prove it or deduce it. You just have to, you know, see that it's correct for many systems until it's proven wrong.
I agree.
That's what you are saying. Okay.
That's exactly.
Is it more that it's an accounting and grouping of states that are in your system?
That's right. Exactly. You can count as many as you want.
Well, so this is it's not the axiom. It is you can derive it from the definition of entropy.
That's right.
Just,
Exactly.
Log p log p, summation of negative p log p. It's just a matter of the conditional probability.
Yeah, exactly.
Hanson, so you were suggesting a Wikipedia link. Which one is it? Is it?
Yeah, just look at because I originally I wanted to write down the proof, but of course there's no way you guys can see when I'm writing down. But just looking at the let's see.
Okay, so you are saying that this formula is derivable from the general formula of entropy. That's what you are saying.
Yes.
So Hanson,
yes.
let me check. I got you what you're saying correctly. So you're saying the page number 9, the equation, the right side, the first one is the p's are conditional probability, while the blue ones are the real finer. But the question is, how do we get SK?
Let me hold on. Let me see which one is which. Because
I should direct the question to Professor if that's correct, then the problem becomes the measuring or calculating the subsystem entropy. How do you do that?
Yeah, exactly. That's what we, in our case, we use the DFT.
I see.
So
So-
basically, yeah, on page 8, that the black one, the black summation is the let's say if we computing x and y, right? So that is the x entropy. I mean random variable x and y. Let's say s. In general, I'm talking about this is the most general statement. But the states and microstates and all that. So S, let's say S is a function of random variable x and y, and then the black summation is the entropy of x, and then blue summation is the entropy of y conditional on x.
So, like if you are saying that is derivable from the general formula entropy, why is it being called Zentropy then? Like why don't just call it entropy? You know, normally why do you call it Zentropy? Like why?
That's on slide 10.
Okay.
I think Hansen, I mean, what Hansen just said is the opposite of what I understood. Maybe I got it reversed. So which one is conditional on which? I thought the S in professor's formula is no different from the original one. It's just like a different grouping. That gives
No. This is the smaller system, the microsystem. SK is the smaller, within that smaller system. You have the entropy. But the PK is the bigger system.
That's right. So that's the bigger system is the conditional probability, right? Conditioning on
No.
micro.
Conditional probability is smaller. So the bigger one is the bottom. So x. So y is conditional on x. So given x.
Okay.
Look at
See,
y.
Yeah.
So
it's
y
fine. Okay.
conditional on x is smaller. Yeah.
Yeah, so I think it's very interesting. I will
Actually, I want to point out one paper, but Hansen just talking about Hansen. Let me share the one. I don't know where I can share. In one of the papers, I work with statistics, exactly what Hansen talking about. Actually, the whole equation here is a probability. It's a conditional probability. I think if you go to my website, if anybody goes to the website, go to my group website, and you look at the publication. Let's see what number is that. If you look at the publication, you go to the website. The number is let's see. Let's see. It's number 488. 488. Number 488.
Thank you, Professor.
That paper, my second author of the paper is a statistician. And he actually explained to me about our approach, exactly what Hansen just said.
Okay, so I will read the paper. Thanks, Professor. I have like since you are an expert in statistical mechanics, I would like to ask you one very general question about statistical mechanics. And that is, this question. So, like people usually say that, we do thermodynamics, because the number of, possible microstate is too large, right? So we have to take, average, to get from microscopic physics to macroscopic physics. But my question is, when you do the full, statistical mechanics, what will you get then? Like if you don't do, the average, averaging, will you still be able to get to macroscopic physics? Going completely from a microscopic physics.
That's what I believe Zentropy can do it. I think the existing statistical formula that's on the left side of slide 10, you cannot do it. The reason is because you cannot sample all the pure quantum state. So it's theoretically you can, but not in the practical. Okay. But with Zentropy we have, with DFT basically is one level of homogenization. Okay, it homogenizes electrons basically. If we take the DFT as our starting point, then the Zentropy can predict from the microscale to macroscale. That's my conclusion. That's why I'm so excited about it. I want to go back to the question Hansen about the probability. Is equation 9 in that paper? Hansen, you nailed it. I usually don't talk about that one because not many people are familiar with this one. If you look at the paper, the equation number 9.
Oh, wait. Which paper?
The 488 in my publication list.
Okay, I see
Yes.
your website.
Yeah, you go to my group website, faces.psu.
I'll change it back to paper, the pin.
You go to my website, right? faces.ps.edu.
Hold on. The NAT. Wait. I got the Penn State College of Earth and Mineral Sciences.
Yeah. You go to faces, right? It's my group of faces.psu.edu.
Yeah, PSU.edu. Yes.
Then that's my website.
And then should I look at?
You go to publication.
Research or something?
You go to publications. Then you go to number 488. You search 488.
Actually, I see a picture. This graduate research. Oh, maybe that's the department.
No, you go to faces, right? Faces.psu.edu.
Faces.
Yeah.
Oh, SF.
Yeah, PH. No, PHASE. PHASE.
I just texted you the website link on the direct messages if you go on there.
Oh, Hansen, you made my day. I never use this one much in my presentation. I won't put this one in my future presentation.
Okay. Oh, I got the phases PSU.
If you go to the publications, you go number 488.
488.
You click the DOI number.
Okay, got it.
Then you go to number 9, equation number 9.
Okay, multiscale entropy and its.
That's right. That's right.
Its implications to critical phenomena emerging from.
Yeah.
Okay.
Equation 9 is exactly what you're talking about. It's about the conditional probability.
Right. Yes. Yeah. So equation 9. Yeah.
It actually, this guy, it's a statistician, he inversed my problem even, right? With from low scale to high scale, he said from high scale to low scale, same thing. He proved that.
Yeah.
That's equation 13 and 15.
Yeah. Actually.
So then what I said earlier is also correct. Is that okay? By the way, Hansen is our in-house physicist.
It's fantastic. Okay, it's fantastic. You guys just wonderful.
I think Jake had one question. He texted me a while ago.
Okay.
If you have time for one more question.
Yeah, go ahead.
Hi there. Thanks for the room. I always appreciate it. I have a question. I'm of course not a professional in this at all. I was just curious if a black hole is really just a photon star, like a collection of photons, since photons don't have mass, but they do have gravity. would it be possible for a black hole to just kind of become a huge collection of photons?
I think
My
it's
understanding is it's the inverse of that potentially.
okay. If you ask, because again, I have to say I'm not a cosmologist, okay, but I can give you my understanding of it. How about that? Okay, so my understanding is like this, right? In my new paper just published, I talk about the quantum criticality. Okay, so quantum criticality is so interesting. So if it basically says that you have at 0 Kelvin, you have the critical point. Okay, so what happens is that if we approach that critical point, and then you see divergence. If you go away from that critical point, you see the divergence disappears. Okay, so it could happen that we had a big bang, we had a black hole. So it's just the two sides of the one singularity. That would be my answer. I don't know. I really don't know more than that.
It's actually really interesting in terms of astral imaging from all of the available space-borne observatories. There are only theoretical models, and there have been some, like there was one image recently, but it was very rough. So it's a little hard to describe right now beyond theory and equations.
That's right. But I do believe that entropy has to have this multi-scale integration together. You want to talk about the entropy of black hole, unless we're talking about the pure quantum state.
Dr. Z, I have a question about I came late here, but it's quite interesting. I was just wondering, it would seem that one of the implications of what you have here would be also, and I'm wondering if you have any comments or thought about it, is a more fundamental explanation of convection. Is that something you've looked into as a
No,
result?
I have not done that. I fully agree with you, because the reason is because convection is a spontaneous process, right? It's the irreversible process, so to speak. And if you think about this continuous convection, okay, that means you have to put some energy into it. So you have to really define your ensemble. But I think many people, when they start that problem, they didn't define the ensemble to study. The reason is because they cannot fix completely the interaction between that system and the surrounding. That's a challenge, I think. I think if you can define that one, then it should be applicable. All right, sounds very good. Catarina, do you have any more questions, or we're done?
I think you've been talking almost 2 hours. It was such a pleasure to have you, and you gave such a great presentation. We learned a lot from you, so thank you for sharing all your
Oh, we get 129 people here, and I saw that.
Yeah, we had a total of 129, and
Wow.
yeah, thanks for coming. Always come back anytime. I hope you will come back and maybe participate in rooms or come back and explain us some more. And yeah, thank you so much.
Okay.
I hope you enjoyed it.
Thank you. Oh, I always enjoy interaction. But for some other people, if you really want to start the process, internal processes, and I have one new paper is accepted for publication. That's 500. Wow, I like the numbers, right? I can see that. Okay. If you are interested to learn, to discuss with me further, that's my 565 paper. 565.
Wow. That's amazing.
Number 565 on my publication list. And that paper, in my opinion, I started working on this one in 2014-15.
Oh, wow. Yeah.
So that paper is like 50 pages, include reference. I just went through the proof yesterday. I submitted the proof.
Oh, congratulations.
Yeah, so the DOI is not working now, but I do have a archive link working for that one. So that one, in my opinion, it's going to be, somebody was asking about, I think it was Chuan asking about applications, right? That paper will show almost all the physical properties were measured, can be predicted.
Yeah, please come back and present it. Let's
Yeah.
email and arrange a time that you're available. That would be amazing to have a follow-up. It's basically a ongoing story then here.
That's right. Okay. All right. Thank you very much. Thank you for the opportunity.
Thank you.
Really appreciate it, Professor Liu. I'm a very advanced research, and you explained it so well. And yeah, well, by the way, you mentioned, thank you for mentioning the exact equation 9, which actually turns out to be what I said earlier. I mean, I guess I understand what Hansen referred to. It's actually the summation of the macro, and then the P is actually conditionally on the, it's the big one conditioning on the small one.
Yeah.
Is that correct?
Exactly.
That's correct.
Yeah, it is.
So Hansen,
Actually, I don't agree.
No, you
Actually, the second term.
you want to look it down there, right?
just look at the equation.
Yes, we switched because the equation, the second term is the first term in the black term in the PPT, and so this is not the conditional. This is the lower the coarser level entropy, and then the SL vertical line K. That is the conditional entropy, and
Maybe
that
we
is
should
the second term of the
invite
term.
Professor Liu to a private
Handsome, is it
special
too like
seminar room. Yeah.
Professor, did your co-author prove they were equivalent?
Sorry?
Didn't you say your co-author proved they were equivalent?
Yeah, that actually, if you look down there, there's equation 9, right? Then equation 13 to, I think, 16. He inversed it. He proved it. The inverse is right too.
Yeah, so that
So
13
there it is.
is, yeah, 13 is the probability that what do we call it, the probability in terms of conditional probability, right? And then 14, 15, or it's the consequence of that. So yeah, I mean it's a joint probability.
Yeah.
Because the conditional probability.
But it's a state function, so how you arrive at it is going to be the same.
Exactly. That's the beauty of thermodynamics, right? It's a state functions. You can go either way, top down or bottom up.
Yeah. So basically, yeah. So this is the but you can decompose the entropy into two parts. One is the whatever baseline, the coarser level, and then the conditional probability. And actually, it goes to the theorem that 16, 17 just kind of shows the consequence. Whichever accounting method you use, it will get the same result.
Yeah. I was very happy. I was looking for that one. I'm not a statistician, so I couldn't prove it. Then he said it's easy. He just grabbed it on paper. He sent to me. That's it. So I put it in the paper. Yeah. So
It would have to be. It would have to be the same, right?
Yeah, exactly. But you have to prove it rigorously. I think that actually is very important. That's 3 authors. You said a paper 3 authors. I wrote the paper. I have the idea. Second person is a statistician. The third person, that's what I mentioned. He worked on forest. He want to predict the wildfires in forest. The instability of forest. He also want to predict when the forest is in good health or bad health. But unfortunately, the life takes so many terms, right? Unfortunately, the third author passed away the same year the paper was published. So we didn't continue that direction. If some of you want to start this ecosystem, we can work on that. I think I know that many people doing neuroscience here, right? Catarina is a neuroscientist. If you guys want to start the biology, application. That'd be fantastic. We can think about how to work together.
Yeah. Yeah, actually, maybe, yeah, that's a good actually idea of, that was actually my idea for future rooms, that I was thinking about bringing different people together that may be interesting to talk together, but even then in the future collaborate with each other. So I thought that would be very interesting for the future to have like this type of discussions, like, so yeah.
Okay.
That's interesting. We should chat more and maybe invite people from ecology, maybe Eli that I know, and some other people would be interested. I was at the Marine Biological Laboratory, and then there, the Oceanographic Institute in Woodsole on Cape Cod, they had actually also a team looking already back then with drones over the color of the leaves in different seasons to calculate how climate change is changing that and things like that. Yeah, maybe we can invite people from different fields for application for your theory. That would be very interesting.
That's right. Okay. Now, well, I want to thank everybody. I got to go, and thanks a lot. Enjoy.
Thank you so much. Thank you.
Okay. Bye.
Bye. Thanks.
Bye.
Yeah, thank you so much everyone for coming and participating in this